polynomials. We write them as px equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 plus a1x plus a sub 0. The exponents are non-negative integers and the coefficients are any real number. The domain of a polynomial is the set of all real numbers. Here are some examples of polynomials. 5x to the 4 plus 8x to the power of 2 minus 7x plus 1. 4x to the 10 minus 28x to the 5 minus x. We usually write polynomials in a descending order, from the highest exponent to the lowest. Here is the polynomial checklist. 1. All the exponents are non-negative integers. 2. All the coefficients are real numbers. Example: let's observe that the function f(x) is a polynomial, and here's the reason. The exponents are 4, 2, 1, and 0. Pay attention. If you look at the pi, this is pi times x to the 0. All the exponents are non-negative integers. All the coefficients are real numbers. E is a real number, so is square root of 2, 7, and pi. Another example. This is not a polynomial, and the reason is because one of the exponents is negative 1, and negative 1 is a negative integer. Example. Let's go over the checklist. The exponents are 3, 2, 1, and 0. All exponents are non-negative integers. Here is the list of the coefficients, and you can see that we have two coefficients which are not real numbers. It's a square root of negative 1 and I. We conclude, then, that hx is not a polynomial. Two polynomials are equal if the matching coefficients for the matching exponents are equal. Let's take now two polynomials px and qx, and let's assume that they are equal. Then, we know that because the matching coefficient for the matching exponents are equal, 5 has to be equal to a, 3 has to be equal to b, negative 2 has to be equal to d, and 5 equals to e. We have only a little problem with the c. But c is 0, because px also can be written in descending order to be 5x to the 4 plus 3x cubed plus 0 times x to the power of 2 minus 2x plus 5. Rational functions. Rational functions are functions that are written as a polynomial or a polynomial. The domain of Rx, a rational function like this, is the set of all real numbers such that Qx is not 0. Example. Here is a rational function, because you observe that you have a polynomial over a polynomial. Is this function a rational function? No. Why not? Because this one is not a polynomial. Exponential functions with base a. Exponential functions with base a are the functions a to the power of x when a is greater than 0 and a is not 1. Pay attention here that the variable is in the exponent. The domain of this function is the set of all real numbers. Example: the function 5e to the power of 3x is an exponential function with base e. Here is the checklist for exponential functions of base a. 1. The variable is only in the exponent. 2. The base is the number a. Example: fx equals 2 to the power of 3x plus 5. 1. The variable is x, and it only appears at the exponent. 2. The base is 2. We conclude that this is an exponential function with base 2. Is the function x to the power of 3x plus 5 an exponential function? One, the variable is x, and it is in the exponent, but not only there. It's also kind of the base, but the base has to be a constant number. We can conclude that this is not an exponential function. Be careful. The function Lx equals x to the power of 3x plus 5 is neither an exponential function nor a polynomial. It belongs to the family of functions of the form fx to the power of gx. Here are some examples: sin x to the power of cosine x, x to the power of 3x, x to the power of tangent x. Piecewise functions. Here is an example for a piecewise function. Fx equals 3 different things at 3 different domains. When x is less than 2, f of x equals the function x to the power of 2 minus 1. When x equals 2, f of x is just 5. When x is more than 2, fx is 2x plus 1. This is the domain of each one of the pieces, and this is what you should apply to each x in the appropriate piece. For example, f of negative 2, because negative 2 is less than 2, I have to apply x to the power of 2 minus 1, and I get that f of negative 2 equals 3. F of 0. 0 is less than 2, so I have to apply again the function x to the power of 2 minus 1. So it's 0 to the power of 2 minus 1, and I get negative 1. F of 2. On the domain x equals 2, f of x equals 5. So this is 5. F of 3. 3 is more than 2, so I have to apply the function 2x plus 1, and I get 7.